In this video, we will review the velocity and acceleration analysis of crank slider mechanism. And we have this position diagram showing the convention that we have been following in the class. This is 2, 3, 4, and 5. And we said the loop closure can be written as R2 minus R3 minus R4 minus R1 equals 0. From here, we can expand this as a e to the j theta 2 minus b e to the j theta 3 minus c e to the j theta 4 minus d e to the j theta 1 equal to 0. And we know that the distance d, which is from here till here, is varying as the slider moves from the current position to the next position. We know also that theta 1 is being set to 0 degrees and theta 4 is 90 degrees. We did this in position analysis. So we can take the loop closure, write it as j theta 3 since c e to the j, we leave it as theta 4 for now, but this is a fixed position and we have t equal to 0. We can take the time derivative of the loop closure equation and obtain j a omega 2 e to the j theta 2 minus j b omega 3 e to the j theta 3 minus this term d dt is 0 because this is a constant now, and we get d dot that should be equal to 0. In other words, what this represents is this is velocity of the position, velocity of the point A, and this is velocity of the point A with respect to A with respect to B, and then we can subtract VB in order to get 0. That's because this point B has only one velocity, which is going in this direction or this other direction. And if we draw this effective link, there's always this velocity of we can draw velocity of point A with respect to B as something which is here. We can also draw velocity of A with respect to the origin as this guy. Now this is velocity of B. And then we can either say VA with respect to B, or we can say VB with respect to A. So we can write VB is VB with respect to A plus VA, or this term is minus VAB. And so we can write VA minus VB minus VA minus VA with respect to B minus VB is 0, which is what this is. We can draw the velocity triangle and confirm that this is exactly what we get. We can start with the origin. We have VA, which is fully known. For an input, omega 2 is given. We know that the velocity of B is along a line which is horizontal here, and we know that from this point, with respect to this point, the velocity of B with respect to A is along this particular line or axis, and so I can draw that. And so this is the intersection, and we can say this has to be VB with respect to A. This has been VA all along, and this becomes VB. We can continue to expand the real and imaginary parts of the velocity difference equation. Um, we have minus A omega 2 sine theta 2 plus B omega 3 sine theta 3 minus D dot is 0. And the imaginary part is A omega 2 cos theta 2 B omega 3 cos theta 3 equals 0. From here, we can obtain expressions for d dot and omega 3, which are the two unknowns. We can solve simultaneously to get omega 3 is a by b cosine theta 2 divided by cosine theta 3 omega 2, and d dot is minus a omega 2 sine theta 2 plus b omega 3 sine theta 3. From here, we can write the absolute acceleration of absolute velocity of A is A omega 2, which we already knew, this sine theta 2 plus j cosine theta 2. We can write VA with respect to B is simply B omega 3 minus sine theta 3 plus j cosine theta 3. And we have V of B absolute is equal to d dot. And we also know that V of B with respect to A is equal to minus V of A with respect to B. Then if we want to consider the other way around, where we know the slider's velocity and we are trying to find the angular rotation of the crank, then we can again start with the same equations as these. So these are the same equations which we will use for the case of a slider crank. The previous one was crank slider. Here we know d dot. We are trying to find omega dot and omega 3. So we can write again omega 3 is still A omega 2 cos theta 2 divided by B cos theta 3. And then we can substitute that into the first equation and obtain omega 2 as d dot cosine theta 3 divided by A times cosine theta 2 sine theta 3 minus sine theta 2 cosine theta 3. And that is as simple as it is. So for acceleration analysis, we can take the derivative one more time of the velocity expressions, and we'll find that we get d dt of velocity equation will give us j a alpha 2 e to the j theta 2 j square a omega 2 square e to the j theta 2. This is coming from the first term, which is here, and then we can similarly take the derivative of the second term to get j b alpha 3 e to the j theta 3 plus j square b omega 3 square e to the j theta 3. And then lastly, we will have a d double dot term, and this whole thing will be equal to 0. So we can then simplify. We can write the real and imaginary parts. We can simplify, and then we obtain um, well, before writing the real and imaginary parts, if we just simplify this, we obtain a alpha 2 e to the j theta 2 minus a omega 2 square e to the j theta 2. There should be a j in the first term. Then we have minus b alpha 3 j e to the j theta 3 minus b omega 3 square e to the j theta 3 minus d double dot equals 0. So what we essentially got is acceleration of a minus acceleration of a with respect to b minus acceleration of b equals 0. We had this as the tangential term, this as the normal term for acceleration of a. Similarly, we had this tangential and this normal terms, and then um, this was simply the tangential term. There is no normal term in the sliding case. Now we can separate this out into real and imaginary parts and obtain the unknowns. In the case of crank slider situation, we know omega 2, we will know alpha 2 because that's the input. We need to find out alpha 3 and d double dot. Whereas in the other case where we are doing a slider crank linkage, we would know d double dot. We would have to find out alpha 3 and alpha 2. So here are the real and imaginary parts of the equation. We can directly write alpha 3 in terms of alpha 2 and other known quantities. In the crank slider mechanism case, alpha 2 is known, so we can obtain alpha 3 and then d double dot from the first equation. In the case of slider crank, d double dot is known. Solving for alpha 3 and alpha 2 is what we want. And so alpha 3 is obtained already. Alpha 2, alpha 3 is the same equation. You can get alpha 2 as a omega 2 square, a cosine theta 2 cos theta 3 plus sine theta 2 sine theta 3 minus b omega 3 square plus d double dot cosine theta 3 divided by a cosine theta 2 cosine theta 3 minus sine theta 2 sine theta 3. Here obtain d double dot from first equation. This is the case of crank slider. Alpha 2 is known. So this is all possible cases of slider crank slider with offset, where we have just shown different acceleration and velocity analysis in the analytical method. For the sake of completion, we can also quickly talk about the acceleration diagrams, and we know this is what we saw as the position configuration of the position. So we can see here we will have, for let's say there is omega going this way, there's alpha going this way, Then there is a tangential acceleration which goes this way, which is a of t, and there is a normal acceleration which is a of n. Then there is this slider where the acceleration has to be along this line. This will have to be the line of b tangential, which is nothing but d double dot. And with respect to this point, we can talk about uh, a tangential acceleration. Let's from A to B. Let's talk about the tangential acceleration of point A with respect to B. So this has to have a velocity and it will go in certain direction like this. And then we know that it has to have normal acceleration in this direction, considering this is the center. So this will be A of A with respect to B normal, and this is only the line of acceleration of A with respect to B tangential. For completion, we will also look at the graphical method for the acceleration. So here is the slider crank. This is the axis. From here, we know the so this is for acceleration analysis. So we already know the omegas and the positions, and we have an input. We can consider the input to be alpha 2. That will make this a crank slider system. So we can identify that there is a tangential acceleration, there's a normal acceleration to point A. We know the magnitude and direction of each of these. At the point B, we can consider that the slider acceleration has to be along this line. So this is a line of acceleration of the slider, that is point B. We can also have a acceleration of point B with respect to A to be in this direction. This is normal acceleration. And then we know it has to also have a tangential acceleration which will be perpendicular to link AB. So this is line of acceleration of B with respect to a tangential. Now we can put these all on a single diagram and say from here, this is normal, this is the tangential component for A. So this is effectively the acceleration of point A. From here, we can go for a acceleration of point B with respect to A normal, and then draw a line along which we know there should be the tangential acceleration of B with respect to A. We can also draw a horizontal line and say acceleration of the slider should be along this. So we can identify this point and we get acceleration of the slider B, and we get the acceleration tangential of B with respect to A. From here, we can take the tangential acceleration of B with respect to A and divide by the link length AB to get alpha 3. So we finished this where we have a crank slider mechanism. We had the input alpha 2, we obtained alpha 3, and we also have d double dot. Now if we consider the situation where we have the information of the slider, that is we have d double dot, and we are trying to find out alpha 2 and alpha 3, we can consider the acceleration of the slider is given. From here, we can say uh, this is acceleration of B tangent here, tangential. We can look at acceleration of the point A with respect to B, in which case we'd have to consider an acceleration of this form. This would be acceleration of A with respect to B. Then we also know from here we have an orthogonal direction. We can find t of A with respect to B. On the other hand, we can draw acceleration normal acceleration of point A in the absolute sense, and we know there is a dashed line describing the acceleration of uh, tangential of A. So perhaps I've drawn this too much oblique. So we'd have something like this, and then something like this to represent this point being acceleration tangential of A with respect to B, and this being acceleration AT of the point A in the absolute sense. Note that I've marked here accelerations of A with respect to B instead of B with respect to A, so it is following acceleration of A minus acceleration of A with respect to B minus acceleration of B is 0. That's the loop equation here. Here it is the same equation, except I've written it in the form acceleration of A plus acceleration of B with respect to A minus acceleration of B is 0. So yeah, again, here now we can identify from AT of point A divided by the link A gives alpha 2, and AT of A with respect to B or B with respect to A, we're considering the magnitude, so it doesn't matter which. This is alpha 3. And that completes the graphical analysis, acceleration analysis of the system as well.